Alright, welcome back everybody. In this video we're going to look at the last couple of examples from the length of polar curves lesson, which deal with finding surface areas of regions that are generated when we revolve polar curves around the x-axis or the y-axis. If you remember back when we did this for parametric curves, if we revolved a curve around the x-axis, we used this formula, 2 pi y times the arc length. And if we went around the y-axis, we used 2 pi x times the arc length. This gives us a great deal of insight into what we're doing with our surface areas for polar curves. Okay. The first thing we need to do is we need to look at the curve tracing exactly, traces the curve exactly once as theta runs from alpha to beta. So we're going to have to make sure we look at the curve and see that we're tracing it only once over a given angle interval. Then in order to find the areas of surfaces generated in these ways, to do revolution about the x-axis, it's just going to be 2 pi times r sine of theta times the arc length. And the reason why is, remember, that y is equal to r sine of theta. And so really this is the same formula. It's 2 pi y times the arc length. And going around the y-axis, remember that x is equal to r cosine of theta. And so this is really 2 pi x times the arc length. All right? So there's our formulas for finding areas of surfaces of revolution. Let's go ahead and look at a couple of examples here. Let's look at example 3. We're going to find the area of the surface generated by revolving the right-hand loop of r squared equals cosine of 2 theta about the y-axis. All right. So, the first thing I'm going to do is take a look at this curve. It's the curve r squared equals cosine of 2 theta. So I'm actually going to need to plot two graphs here. R equals square root of cosine of 2 theta, and r equals negative square root of cosine of 2 theta. And so we're going to graph this and take a look at what it looks like. Gosh, I guess that's all I got. Let's go back out to a standard window here. Oh, that's even worse. What happens here is basically we're looking at this right-hand loop, and my graphing calculator struggles to graph it, but we're looking at this loop over here, and revolving that around the y-axis. Now in order to do that, I'm going to try and make things a little easier on myself. Let's see, if I trace this first curve, r equals the square root of the cosine of 2 theta. It jumps there for me when it didn't connect it, but it should. It should be going from 0 to pi over 4 for my angle. And then that gets the top half of the right-hand loop. So I'm going to actually double that in order to get the surface area revolving around the y-axis. So I'm going to take 2 times the integral from 0 to pi over 4. Okay? And then I need 2 pi times I'm going around the y-axis, so 2 pi x. So I'm going to take that original 2 and I'm going to multiply it by the constant from 2 pi. And then x is equal to r cosine of theta. And r here is the square root of the cosine of 2 theta times the cosine of theta. And then I need the arc length. I need r squared plus dr d theta squared. And if I take the derivative of this, r equals square root of cosine of 2 theta. The derivative of that is going to be dr d theta equals, let's see, 1/2 times cosine of 2 theta to the negative 1/2 times the derivative of the inside, which is negative 2 sine of 2 theta. And simplifying all that, we get that dr d theta is, let's see, negative sine of 2 theta over the square root of cosine of 2 theta. So we're going to take that and square it. With respect to theta. And now I'm going to go ahead and calculate that. I've got 4 pi times the integral of square root of cosine of 2 theta, close the square root, times cosine of theta, times the square root of cosine of 2 theta plus quantity negative sine of 2 theta over square root of cosine of 2 theta, close the parentheses, close the square root, close the quantity, square it, close that square root. I think I've got all my parentheses in there. Go ahead and let my calculator calculate this value for me. And I get 8.886. Notice how I was careful to find the upper limit of integration that was necessary, and I doubled it in this case since I only used the top half of the curve in order to find the surface area. Alright, find the area of the surface generated by revolving r equals square root of cosine of 2 theta about the x-axis. So this time we're going around the x-axis. We're given our limits of integration. If we look at the curve, this is actually just the top curve here. That curve, and again, remember it's missing a piece. So we're just going to revolve that from 0 to pi over 4. So we've got 2 pi times the integral from 0 to pi over 4 of y, which is r sine of theta. So square root of cosine of 2 theta times the sine of theta times the square root of r squared plus dr d theta squared. It's the same dr d theta, negative sine of 2 theta over the square root of the cosine of 2 theta, all with respect to theta. And now I'm going to go ahead and calculate this. I'm just going to take the entry that I have before and edit it. This should be 2 pi, 2 pi times the integral of square root of cosine of 2 theta sine of theta times the square root of cosine of 2 theta plus that quantity squared with respect to theta from 0 to pi over 4. And so the surface area of this region ends up being 1.840. Alright, that's the end of example 4 and the end of this lesson. I'd say see you guys next time, but guess what? This is the last video of the course. You've reached the end of AP Calculus BC and the instructional videos that go along with it. So I won't see you next time, except for maybe in real life, those of you who are in my class. I hope you've enjoyed these videos and that they've been helpful to you in succeeding in this course, and best of luck to you in the future. Alright, have a great rest of your day.